Okay, question number 7. H is this logarithmic graph, and the inverse is being given to us as well. So let's type them in. Okay, so new line. I've got 1/8, get myself out of the way there. So 1 divided by 8, and I'll open up my bracket. And inside the bracket, I've got log base e, so ln, x, close that bracket. I've also got a bracket x here, and it should be 1/8 of, yep, that's good. And I've also got fraction, I've got e to the 8x, so that's a plus 1, xe, and what will it look like? There is that one, there is that one, and we might look at it just inside here. Okay, beautiful. State the equation of the asymptotes of H. H has asymptotes at x equals negative a half and x equals positive a half. The inverse will have y equals negative a half and y equals positive a half. State the coordinates of the intersection points of h of x and the inverse to two decimal places. I can see the 0, 0 is one of them. Analysis G-solve intersection, negative 0.48 and negative 0.48. And the other one I suspect will be positive 0.48, and it is. Two decimal places. So the gradients of the h, so the gradient of h at x equals 0 and the gradient of the inverse of h at x equals 0. So if I take this expression here and put it into a new line, and I bring up the derivative with respect to x, and outside here I say math 3 given x equals 0, it will give me the gradient is a half, and that was of the logarithm. So this one should be a gradient of 2 if it's the inverse, because the x and the y flip around. But just to confirm, what I might do is I might take all of it. I'll take all of that. Put that into a new line. Get rid of the inside. Get this, put that on the inside, and set it equal to 0, and I got 2. And now I've got to draw a graph. And on the tablet it's going to be difficult, so blue. So I have an asymptote at x equals a half, and x equals negative a half. So x equals negative a half and x equals a half. And I know that at 0.48, 0.48 is a point that it goes through, and negative 0.48 and 0.48 is at a point that it goes through. It's going to look like, keeping in mind I'm also drawing the blue curve over there, and it's going to have a gradient of a half, so it's going to be quite not as steep. I don't have a pencil here, but you get the idea of what I'm drawing. And I'm going to call that h of x in blue. Then I'm going to change my colour, pick up my red pencil, and the other one's also going to go through the same 3 points. It's going to have an asymptote at y equals negative a half and y equals a half, and the curve's going to have a gradient of 2 there. Look like this, and look like this, and that's going to be at negative 0.48, 0.48 negative. That's going to be 0.48, 0.48. That's going to be at 0, 0. And that's going to be the inverse of H. Labelled, asymptotes labelled, intersection points labelled. Okay, that's good. Now over the page, I'm going to consider G, where I don't have 1 on 8, but I've got 1 on K. And the inverse of G, I don't have 8 there and 8 there, but I've got K. So we've got this graph. This is the example when K equals 8. State the gradients of the G and the inverse at the origin. Okay, so I'm now going to turn that into A and turn that into K. And luckily I kept the other one. That's going to be 1 on K. And when I press XE, I get 4 on K and K on 4. So 4 on K and K on 4 is the gradient of so K on 4 is the exponential. So this is of G, and this is the gradient of G negative 1, both at x equals 0. Here's the graph of 2, there's no overlapping. Here's the graph of 6, we now have overlapping. Here's the graph of 10, we now have overlapping. Here's the graph of 8, we have overlapping. So this is a kissing function, and it's a kissing function because I've got a logarithm and an exponential. And a logarithm and an exponential will just touch when the gradients are equal and the gradients equal 1. So for the gradients to equal 1, K has to equal 4. So I want K to be bigger than 4 because when K equals 4, I will have one of them and the other one, and it will just touch and there'll be nothing overlapping. The minute we get bigger than 4, we'll then have overlapping. Okay, when K equals 6, so if I was to go back up here, so K equals 6 and K equals 10, neither of them were K equals 8. So if I come back up here and redraw these, so how about I pick up this one and make that 6, make that 6, and make that 6. And if I touch there and press XE, then I go back up, there is that one, drag and drop. There is that one, drag and drop. And analysis, G-solve integral intersection, select the first one, accept it, jump over to the last one, accept it, and the trapped area is 0.076, how many decimal places? 2, 0.08. And for 10. So I'll go back up and do the same thing. Now, the reason that we're doing these is we're getting an idea of what's actually happening each time. So the author of this question has got you to look at 8, 6 and 10. There is the 10. There is the 10. And if we look at analysis, G-solve, integral, intersection, accept the first one, accept the last one. The combined area is 0.26. .23. Okay, so we have asymptotes at a half and a half and a half and a half. And the bigger that my value of K is, then my asymptote is going to get closer and closer to the asymptote. and the inverse will be this one here. So the combined areas will each approach the inside square. The square that's determined by a half and 0 and 0. So a half times a half is 1/4, and a half times a half is 1/4. So the combined areas are going to approach 1/2. As k gets bigger, then the curves get closer and closer and closer to the asymptote, so that the combined areas will fill those squares. So the area will go from 0 when there's no trapped area up to 1/2 when it's a full trapped area. That's how question 7